Hello. So today we are going to present our paper about utilizing SVM and noise bias to detect hate speech in Twitter. This paper is written by me, Andrew Nicholas, and my partner, Kenneth Suryapermana, and Miss Jurika Moniaga, and also Miss Gina Zainabila. So the topics that will be presented in this presentation are introduction, literature review, methodology, results and discussion, and conclusion.
Okay, so for the first topic of introduction, hate speech on social media have a lot of problem in society. In 2021, a number of 40% of the US society has experienced online hate speech. Nowadays, social media platforms and Twitter, in particular, are vital components of contemporary communication. They make people able to share their point of view and engage in public debates. Nevertheless, the growing popularity of such platforms has resulted in complex problems, one of which is the spread of hateful speech and inappropriate materials. Hence, there is a need of development of an auto model which can detect such harmful content online. Okay, for the second section of literature review, for knife bias analysis in Twitter hate speech, some prove that using knife bias with TF-IDF and NGRAD features get an accuracy of 82.13%. This accuracy was based on their topmost optimal performance. However, this research data is used in Indonesian language tweet data. This paper compares the knife bias algorithm using multiple models, such as with multinomial Bernoulli, Gaussian, and gram and ratio data 80 to 20. The second most high accuracy was Bernoulli knife bias with an accuracy score of 0.6337.
So for the methodology used, first, we do dataset collection, and then we do data pre-processing, and then feature extraction, and then train test split, and then model training for knife bias and SVM, also model evaluation for knife bias and SVM, and also we do comparative analysis. So for the first part, dataset collection, the dataset used on this paper is a tweet dataset in which has 6 columns, which is polarity, ID, date, query, user, and text. The polarity of the tweet is between 4 and 0, which means 4 is positive and 0 is negative. Date is the date of the tweet, user is the user of the tweet, and text is the tweet itself. The second part is data pre-processing. The pre-processing of the text data is a crucial step because it makes the raw text ready to be mined. For example, it will be easier to extract information from the text and apply machine learning algorithm to it. The pre-processing step aims to remove inconsistencies, noise, and irrelevant information from the data, making it more meaningful and easier to work with. The third part is feature extraction. Machines can't understand words and characters. In order to make machine understand, we need to convert words into integer or floating points for use input. This process is called feature extraction. The fourth part is train test split. The train test split is an elementary operation in machine learning to evaluate our hate speech detection model's efficiency. We use 80% of the annotated Twitter dataset for training, while the remaining 20% is for testing purpose. This allows the model to learn on a significant proportion of proper data to recognize features and patterns, while the rest would be used to assess its generalization abilities. The fifth part is model building. Support Fortune vector machine is a supervised machine learning algorithm that usually used for classification. Knife bias model is trained by calculating the probability of a feature given a class and further using probabilities for feature predictions. And the last part is model evaluation. Once the models have been trained, model evaluation becomes a critical step in which the trained models are subjected to the test dataset to determine their performance. The key metrics used include recall, F1 score, precision, and accuracy. The fourth part is train test split. The train test split is an elementary operation in which machine learning to evaluate our hate speech detection model's efficiency. We use 80% of the annotated Twitter dataset for training, while the remaining 20% is for testing purpose. This allows the models to learn on a significant portion of proper data to recognize features and patterns. while the rest would be used to assess its generalization abilities. The fifth part is model building. We use support machine factor machine, and support factor machine is a supervised learning algorithm that usually used for classification. Naive Bayes model is trained by calculating the probability of a feature given a class and further using these probabilities for future predictions. The last part is model evaluation. Once the model has been trained, model evaluation becomes a critical step in which the trained models are subjected to the test dataset to determine their performance. The key metrics used include recall, F1 score, precision, and accuracy. Now we will discuss result and discussion. This is the conclusion matrix for SPM and also naive Bayes. When comparing the performance of SPM and naive Bayes, we find that SPM achieved a slightly higher true positive rate of 38.86% compared to naive Bayes 36.91%. This indicates that SPM had a better ability to correctly identify instances of positive claims. On the other hand, naive Bayes exhibited a higher true negative rate of 38.93% compared to SPM 37.09%, suggesting a superior capability in correctly identifying instances of the negative class. In terms of false positive rate, SVM had a rate of 30%, signifying that it incorrectly classified a higher proportion of actual negative instances as positive. In contrast, live bias had a slightly lower false positive rate of 11.16%, indicating a lower tendency to misclassify actual negative instances. Lastly, SVM demonstrated a lower false negative rate of 11.05% compared to knife bias 13%, implying that SPM had a relatively lower likelihood of classifying actual positive instances as negative. These differences in performance metrics provide insights into the strengths and weaknesses of SVM and knife bias in correctly classifying hate speech instances and avoiding misclassification. This is the result of training accuracy, testing accuracy, precision, recall, and F1 score. SVM achieved a higher training accuracy of 93.90% compared to knife bias, which achieved a training accuracy of 86.86%. This suggests that SVM was able to better fit the training data and capture the underlying patterns or relationships between the features and the target classes. A higher training accuracy indicates that SVM was able to correctly classify a larger proportion of instances in the training set. On the other hand, when it comes to testing accuracy, both SVM and knife bias achieve similar performance levels, with SVM achieving a testing accuracy of 76.002% and knife bias achieving a slightly lower testing accuracy of 75.69%. This indicates that the generalization ability of both algorithms was comparable on unseen data. Now we go to conclusion. In summary, SPM demonstrates a high training accuracy, suggesting a better fit to the training data, while knife bias exhibited a slightly lower training accuracy, but a comparable testing accuracy. These differences indicate potential disparities in the ability of the two algorithms to generalize to unseen data and their respective trade-offs between complexity and flexibility. The precision and recall values demonstrate that SPM not only correctly identifies a high proportion of actual hate speech, but also minimize false positive, making it a reliable choice for content moderation. So that's it for our presentation. Thank you for listening. Bye-bye.